And next, the generating function for negative binomials, and I'll also tell you why the negative binomial distribution is actually called negative binomial. To find the generating function for negative binomial, I'm going to borrow a fact from analysis, a definition and a fact. So the fact actually starts with a definition. Fix any real number and a positive integer m. I'm going to define the binomial coefficient alpha choose m for this scenario. Okay? And here's how I'm going to do this. So what is n choose m? N choose m is n factorial over m factorial n minus m factorial if everybody is a positive integer. And actually I can cancel out a lot of products from n factorial and n minus m factorial. What is left is n minus 1 down to n minus m plus 1 over m factorial, because everything else cancels out if I just expand the two factorials, n factorial and m minus m factorial. And this way of writing it makes perfect sense if I replace n by a real. So the definition of my binomial coefficient is going to be alpha times alpha minus 1 times dot 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 alpha minus m plus 1. M is an integer, that's important, but alpha is not necessarily, over m factorial. That's the definition of alpha choose m for any real number alpha, and it makes perfect sense. If alpha happens to be a positive integer, then we see on the right hand side that it gives me back the usual binomial coefficients which we learned a long time ago. In particular, I can now, before I do my calculation, I want to mention Newton's binomial theorem. That's the fact. Newton's binomial theorem actually still holds for this setup. Okay, take a sum of alpha choose m and x to the m and y to the alpha minus m, and this time m will go from 0 to infinity. Okay, assume as well that x over y is actually in absolute value is smaller than 1, so that this thing can be actually summed up, that this thing will converge. In that case, the infinite sum is x plus y to the alpha. Now, this is clearly a generalization of the binomial coefficient for integer, for the binomial theorem for integers. If n is an integer, then n choose m is going to be 0 as soon as m goes above n, and that's easily seen from this definition here, or if you want that definition here, if alpha is a positive integer, if m exceeds alpha, then this product will have a 0 in it, so the thing goes to 0. However, if alpha is not an integer, then this is not the case, and alpha choose m will stay positive or possibly negative for higher m's, and therefore I need to look at an infinite sum here. Other than that, Newton's binomial theorem works as it works for the classical case. But of course I have to be careful with convergence issues, and that's why I'm assuming that x over y mod is less than 1. Okay, so once we have this, then I look at minus r choose m, because that's going to be useful for us. So minus r choose m. What is minus r choose m? So the definition is minus r minus 1 minus r minus 2 dot 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 minus r minus m plus 1 over m factorial. And notice that it's always up here, I always have m terms, and here as well I have m terms. M is an integer, positive integer. Okay, now I want to factor out a minus 1 from each of those terms. So I'm going to say minus 1 to the m and then change the sign for each of them. And actually this was the smaller, but if I factor out the minus, this is going to be the larger of them. So I'm going to start with the last term, which is r plus m minus 1. The one beforehand was one larger, but with the minus sign it's now going to be one smaller, so it's that. And it goes down all the way to r plus 1 and r. R plus 1 and r. Okay, so with the minus 1s factored out, I get to this point. Now, if I look at very carefully this formula, then I see that I start with r plus m minus 1 and I go down in the factorials m steps and I divide by m factorial. That's actually in the form of a classical binomial coefficient. So if I very carefully look at that, then I find that r plus m minus 1 choose m is exactly what I have, because I have r plus m minus 1 times r plus m minus 2 times down to r over m factorial. It doesn't even need to be classical at this point, but that's what I have. So it is classical indeed, classical integer binomial coefficient if r is at least 1 and integer. Then I have an integer here which is larger than or equal to the one below. It's a very classical binomial coefficient. As such, it even satisfies the symmetry condition, namely something choose another thing is the same thing choose the top one minus the bottom one, so I can do r plus m minus 1 minus m, which gives me r minus 1 down here. So an interesting feature about these binomial coefficients is that I can change the negative sign up here. If r is at least 1, I can change the minus sign in front into this kind of classical binomial coefficient at the expense of a minus 1 to the m's power. That's a very useful thing to know, because with that I can now actually come to the binomial, the negative binomial generating function, negative binomial parameters r and p generating function. Okay, so let's refresh what we had on the negative binomial. It's a nice mass function, and we're just going to use the mass function in a second. And we also remember from kind of a geometric or probabilistic proof that the negative binomial is actually the sum of independent geometrics, optimistic geometrics. But I don't want to use this here. What I want to do instead is find this generating function. Okay, now the negative binomial can be go from r up, because it's waiting time for the r's success in IID trials. So I'm going to go from r to infinity with the mass function, and I have to multiply that with s to the I. Now what is the mass function? I'm waiting for the r's success, and that should come at the i's trial. Beforehand I have r minus 1 successes in the previous I minus 1 trials, and I have a total of r successes and I minus r failures. So that's what I want to calculate. Now, I don't like this sum going from r. I want it to go from 0. So I'm going to make a substitution. I'm going to replace r by another summation, namely m is going to be I minus r. And then this m will then go from r minus r, which is 0, to infinity. Then I have s to the I is m plus r, so s to the m plus r. And then I have p to the r, that stays, q to the I minus r, which is just m. And then I have I minus 1, which is m plus r minus 1. Choose r minus 1. Okay. That's what the substitution gives me. And now you start making a connection here, I suppose. M plus r minus 1 choose r minus 1 is exactly what I have there. So actually this will become the sum from 0 to infinity of s to the m plus r. Now s to the m plus r, actually what I want to do with that is I don't really need the s to the r. So I'm going to just write s to the m and q to the m. And I'm going to put the s to the r at the end of it, and also the p to the r at the end of it. So now I have all my powers, right? S to the m, q to the m, s to the r, p to the r. And then I have the m plus r minus 1 choose r minus 1. That will give me a minus 1 to the m times minus r choose m, and also minus 1 to the m. Okay, and yes, and now I have all terms, and writing these constants in front, I can now look at Newton's binomial theorem. I can collapse the s to the q and the minus 1 to the, the sq to the m and the minus 1 to the m. I can collapse them into one term, and I can call this x to the m. And I can also plug in here a 1 to the alpha, which is minus r, minus m. Anything, 1 to any power is 1. So that will give me the y to the alpha minus m term. Okay, so that doesn't do any harm. And then I have the sum of m, alpha choose m or minus r choose m, x, which is sq minus 1 to the m, and then 1, y is 1, to the alpha minus 1. Notice that sq for s equal to 1 is smaller than 1, so x will be smaller than 1, which is y. X will be smaller than y, sq with the minus sum in mod smaller than 1. So things converge, and I can just plug in x plus y to the alpha, which is minus r. What is x again? X is sq with the minus sign, and y is 1. So I end up with sp over 1 minus sq to the r's power, and that's my generating function for negative binomial.